Friends, very good morning to everyone. Today we are going to discuss about disconnection approach. As the name indicates, is an approach which is used for synthesis of molecule or any structure or any organic compound. Any molecule or any compound given, we can analyze that and disconnect that into smaller molecules and join all those together to get the target molecule. This is disconnection approach. It is, in fact, it is the reverse of synthesis. That's why it is also called as retrosynthesis. Thus, we name it as retrosynthetic principles and synthetic applications. Disconnection approach or retrosynthetic analysis is a logical process of analyzing the structure of the target molecule and disconnect them to get the possible synthetic route step by step. This is retrosynthetic analysis. Any molecule given, we try to break this molecule logically. We cannot break the molecule as and how we want. There should be a logic behind the breaking. For having that logic, we need the basics of organic chemistry. If our basics of organic chemistry is perfect, then we can disconnect the molecule to get the starting material and various reagents. And those starting material I'll treat with various reagents step by step and I'll get the target molecule. This is an approach for the synthesis of the molecule. Generally, when we go for synthesis of a molecule, we go for literature survey. What is that? Why we go for this? It is for the fact that if at all anyone have synthesized the molecule before, what approach they have followed. When they have already done it, we follow them. Or we can get a knowledge about that and we can modify that already given synthetic route. If at all it is not prepared at all before, it is not reported, then we have to go to retrosynthesis. Our nature has given enormous number of compounds to us. And this enormous number of compounds have practically n number of applications, starting from pharmaceuticals to medicinal to whatnot. Any molecule like morphine or any other alkaloid or glycoside or anything, the chemist try to synthesize those in the laboratory. Why it is so? because natural products has its own limitation. They are available in very minute quantities. As they are available in very minute quantities, and extracting them is a very laborious task, and more than that, it is a very costly affair. To get the economic viability, we are going to synthesize that molecules. How to synthesize that natural product molecule is by retrosynthesis. Any molecule given, we break that molecule into smaller one to get the starting material. And that starting material we take, add various, treat with various reagents step by step and get this target molecule. In retrosynthetic analysis, we use an arrow mark Vs A with a double lined arrow B. B A with a double lined arrow B, which indicates that B is the precursor for A, means A can be prepared from B. In case of synthetic route, when we mention synthesis, we use a single lined arrow. But here we use double lined arrow in retrosynthetic analysis. Here we use three terms in common. Functional group interconversion we represent as FGI. Functional group addition we represent it as FGA. Functional group removal we represent as FGR. We have to add few functional groups, or we may have to remove few functional group, or when you are not able to add functional group directly, we convert it into another functional group, that is functional group interconversion. In the process of retrosynthesis, we have to do these three things. As disconnection is a conceptual cleavage. You have to cleave the molecule, break up the molecule, and there should be a concept behind it. Conceptually, it have to cleave. And in this process, we break the bonds in the molecule. Why we have to do that? To get the possible starting material. This is disconnection approach. In this, when we cleave the bonds, we will get synthons. Synthons are nothing but the fragments, the broken part, the broken fragment. The synthon can be a DN synthon, means it's a functionalized nucleophile. D represent it is donor. Nucleophile means electron rich species. This excess electrons it can donate. It's a function of DN synthon is a functionalized nucleophile which has an heteroatom in this functional group, and this heteroatom is joined to the nth position of the carbon atom. We also use another term, synthon, that is AN synthon. These are called as acceptor synthon. If it is a donor synthon, it is donating the electrons. Opposite to that is acceptor synthon. Acceptor synthons are functionalized electrophiles. Electrophile, electron loving. Electrons, if it lows, means it is deficient of electrons. It is having an heteroatom in the functional group of this functionalized electrophile attached or joined to the nth position of the carbon atom. And to get these synthons are nothing but the broken fragment after disconnection. To get that fragment, we use reagents. The reagent is nothing but a chemical compound that is used to get that synthon. When we break up the molecule, we get various fragments. We call them as synthons, and they may be donor synthons or acceptor synthons. To get these synthons, we use various reagents. We can give few example for donor synthons. As it is, I said, it's a functionalized nucleophile. Cn minus, it's a nucleophile. It can act as a functional group. This can act as a donor synthon or CH2CHO minus. This is electron rich carbon. That's why it is a donor synthon. Similarly, we can have functionalized electrophiles. I can give few example which is having electron deficiency, a carbon CH2OH. OH is the functional group and the heteroatom is the oxygen. It is attached to the nth position of the carbon plus CH2CHO plus CH2CH2CHO. This all can act as the acceptor synthon, or they are the examples of acceptor synthons. To get this donor synthon or acceptor synthons, we should use various reagents. A reagent is a chemical compound which we are used to get this functionalized synthons. To get various synthons, we can use different reagents. If I need CH3 plus, I should use what reagent I can use. If I need CH3 minus, what reagent I can use. If I want plus CH2, CH2, CHO, which reagent I can use? Means we have to use a reagent which can have CH3 plus. I can use CH3I, methyl iodide. As iodide I minus is electronegative, it pulls the electrons and renders this carbon positive, and that's why it can CH3. If I dissociate CH3I, I can dissociate as CH3 plus I minus, and CH3 plus is the synthon which I can get from using reagent CH3I. Instead of CH3I, I can use CH3O2TS, tosyloxymethane. This can dissociate to CH3 plus and tosyloxy group. These two different reagents for the same synthon can be used. If I want CH3 minus, I can use CH3MgBr, a Grignard's reagent. CH3 minus, as carbon is attached to a metal like magnesium, which is more electron donating than carbon, it donates the electron to carbon, and that's why it makes electron rich. If I dissociate, it gives CH3 minus as the synthon. I want CH2, CH2, CHO plus. I will use CH2 double bond CH, CHO. If I hydrogenate it, I'll get this CH2, CH2, CHO. This is how we can select various reagent for various synthons, and this synthon reagents I treat with the starting material. I'll get the corresponding synthons. And when I join all these synthons, I'll get the corresponding target molecule. I can explain this by taking benzocaine as an example. Retrosynthetic pathway. How to deduce the synthetic route for the synthesis of benzocaine? The target molecule, I have the structure para amino ethyl benzoate. I have this molecule now. I will analyze and I will break the molecule conceptually such that I'll get synthons. When I break, that breakage I'll represent by the wavy line like this. This is carbonyl group, this is ethoxy. CO cleavage is occurring. I represent as a double lined arrow, and in upside of this double lined arrow I'll represent which bond is broken. Carbon oxygen bond is broken. When I break this, what will I get? This part I will take off, this part I will take off. When I break this, I'll get this is one part, another part is OET. This I represent as plus, this as minus. This is a functionalized acceptor. This is a functionalized donor. This is DN synthon and this is AN synthon. Where to keep plus, where to keep minus? As carbonyl carbon, this as electron deficient center because of the electronegativity of the oxygen have to give plus sign over here. O oxygen it is taken as this is plus, this becomes electron rich. To break this molecule, I should have the basic knowledge of chemistry. To write this synthon, which group should get positive center, which group should get negative center, we should have the basic knowledge of chemistry. This to get this synthons, what are the reagents I can use? To get para amino benzoyl derived group, I should use para amino benzoic acid and ethanol. OET minus I can get from ethanol. Ethanol I can use as a reagent. Para amino benzoic acid I can use as a starting material, and I treat the para amino benzoic acid with ethanol. In the presence of sulfuric acid, esterification occurs, I'll get benzoate. This is the logical breaking out of get the starting material and the reagent. Para-amino benzoic acid is not easily available. That's why I have to synthesize this para-amino benzoic acid. Here, carbon, if I break over here, I'll get CO2 and the aniline group. But carbon dioxide is a weak electrophile. It cannot react with this aniline so easily. That's why I have to, as I cannot add directly this COOH functional group, I have to go for functional group interconversion. Means I have to add another functional group instead of CO2, which can be interconverted to get this COOH. This CO instead of COOH, I'll do functional group interconversion. I replace this carboxylic group functional group and add methyl functional group. If I add this methyl group, if I oxidize, I can get carboxylic acid. That's why I can take para amino toluene. Now I can, how to get this para amino toluene or paratolidine? And I can break this carbon and nitrogen. and NH2 is electron rich, NH2 minus, benzene is electron rich. When the benzene and amino group cannot react directly because both are electron rich. As we know, like poles repel each other. Hence, I do functional group. Instead of amino group, I add nitro group. Amino group I have replaced by nitro. Nitration of benzene can be carried out. Right? Now, I'll break up this over here. I represent as which bond is broken. C and N bond is broken. I'll get a synthon. As this is taken, nitro is electron withdrawing. This becomes electron rich and NO2 plus. NO2 plus I can get from using the reagent nitric acid and concentrated sulfuric acid. I can nitrate to give para-nitrotoluene. And toluene is easily available. Toluene, I can nitrate, I'll get para-nitrotoluene. I can reduce this nitro group to get paratoluidine. Then I can oxidize this methyl group to get para-aminobenzoic acid, and para-aminobenzoic acid I can treat with ethanol to give rise to corresponding benzocaine. This is the reverse of synthesis, breaking up the target molecule into synthons to get the starting material and reagents, and combine the starting material toluene and treat with various reagent. I will get corresponding benzocaine. This is all about the simplest form of explanation of retrosynthesis. Let us look into the details in the coming class. Till then, have a nice day. Thank you.